All right, so before we get into things, just one quick, I say reminder, but I kept forgetting. It's kind of a reminder for myself. I kept forgetting to say this. But every Wednesday in this class, we do have a review session hosted by two of our wonderful TAs, Jacob and Logan. They have review sessions Wednesdays, 5 to 7 p.m. On Twitch, and they'll have some content prepared usually, and then they'll take open-ended questions. You can ask them whatever questions you want. Typically related to the course, but if you have other questions too, they'll be happy to answer it, I'm sure, as long as things aren't too busy. For the details and for the link, it's the second pinned post on Piazza right now. Go to Piazza, check that out. They'll have more information for you there, as well as the link. Here comes the dog. The dog's right here, but he's sleeping. So with that, review session, every Wednesday, 5 to 7 p.m. They had it last Wednesday. They had quite a bit of attendance too, even though I forgot to mention it. It is for both sections. I think in the other section, maybe Nazarene remembered to mention it. But check that out. If you want to get more reinforcement with the material, if you just want another way of having things explained, maybe the way I explain things just doesn't gel well with you, have other people explain it to you, get more information. If you're struggling with the material especially, you should be at those review sessions, and they'll reinforce the content that we're covering. Okay, with that, let's do some unit testing. Ooh, boy. I forgot to download the slides. Speaking of, actually, I do have to do one quick thing. I forgot to push. So I got to update I added a few examples to the repository. So I'm going to push those, the really crappy message. I better add a little bit more new testing examples. A little bit more to that. Oh, you can't see that pop up anyway. To push those examples. So if you pull, you'll get the latest examples that I just pushed to the repo. And now we're ready for unit testing. Let me make sure these are the latest slides too. Yeah. Okay. Can we rewatch the review sessions from last week? You should be able to. I went to rewatch one once, and it wasn't in their video, so I don't know if they removed the videos or not. You'd have to ask them. Maybe one of them can answer. So, unit testing. Long awaited, and this is the first brand new topic in 116. So everything that we've done so far, that was all review of 115 content, but in Scala. And really what we've learned so far is Scala syntax. Something you have to know. It's useful stuff. Obviously, if you're going to code in Scala, you have to know Scala syntax, but not interesting from a computer science perspective. You didn't learn anything new yet. This is the first brand new topic, and of course the rest of the year, the rest of the semester, is all going to be brand new topics. So let's talk about unit testing. And when we get into these new topics, you will start to hear me slow down a bit. I'll stop explaining things at lightning speed because it's brand new stuff. I don't expect you to know this stuff already. I do expect you to know what a key value pair is and how to work with those lists and stuff. And I was just explaining syntax. But now, new stuff. Let's digest this and take some time. So your lecture objective today, no brand new lecture objective. We're not moving on to lecture objective 4 until Friday. But we are adding testing. So we didn't do any of the testing of lecture objectives 1, 2, and 3. So that's your lecture objective today. Go back to lecture objectives 1, 2, and 3 and fill out those test suites to do some testing on the code for those lecture objectives. So that's what we want to be able to do by the end of today. Test all 3 of those things. So let's talk about testing. The big question, how do you know if your code is correct? So far in your career, you know your code's correct because you submit it to Autolab or you submit it to UB Infinite, and our graders written by your professors told you whether your code was correct or not. So you really haven't had to think about this much yet. But now, what are you going to do after Autolab's gone? So in your later classes, you might not always have Autolab. in 220-250, Autolab isn't going to give you all of the information, all of the grading information that that you want to know. Automod does not like 191. So it doesn't give you everything that you want to know about your grade, but it will give you some information, but not all of it. And especially after you graduate, there will be no Autolab, there will be no AutoGrader. So as a professional software engineer out there in the real world, how do you know your code is correct? How do you know it's right before you release it to the world full of bugs, and then you get a bunch of customer complaints and you have to manage a disaster after you release buggy software? I'm sure you've used buggy software before. How do we prevent that? How do we know that our code is correct before we release it to our end users? So we're going to revisit an example from earlier in the semester. This compute size method, I think it was like the second example we saw in the course a week ago, last Wednesday. We took in a double and just returned large, medium, or small if that double was a big number, a medium number, or a small number. An arbitrary question to ask. But just for the sake of example, we said above 60, equal to or above 60 is considered large, between 30 and 60 is considered medium, and below 30 is considered small. So just recall this. And we used a conditional as the last part of this method. So whatever branch of this conditional we ended up taking, that was what ended up being returned, since that would be the last expression that's evaluated throughout the run of this method call, either the literal string large, the literal string medium, or the literal string small. So how do we test this and know that it's correct? So what we've done so far, kind of the progression of testing that you've gone through, either you just submit and figure out if the grader gives you points or not. Once you get more sophisticated beyond that, you start writing a main method and start calling your own method. We're going to call compute size on various inputs, print those inputs to the screen, verify with our eyeballs, and use our human brain to figure out if the printed values are the values that we expected. So when this prints large, medium, small, all on separate lines, we're going to say, this passed my testing, cool. But what happens when you have a very large project? The theme of this course is how do we write large programs? So say we have a program that's hundreds of files, thousands of methods, hundreds of classes, and we have tons of code interacting with each other, lots of things going on. Every time we want to test this code, and whenever we add code, we might break things that are not even in part of that code, or we might expose bugs somewhere else in the code base, anywhere in this code base. So when we make a change, or our teammates make a change, because something this big is probably a team project, how are we going to know that that change didn't break everything? If we're using main methods like we did on the previous slide, are we going to run hundreds of files and verify with our eyeballs and our brains that everything was actually printed out as we expected? A project this large, you're not going to do that manually, or at least if you do, you should probably be fired. You shouldn't be in this industry. You need to be automating your testing. So with automated testing, and what we'll see is unit testing, we're going to automate the whole process of testing this large project so we can hit one button, run my tests, and then have the test say whether it passed or not. Instead of verifying if we printed the proper thing to the screen, we're going to automate that process with software, more software to test our software. So unit testing is going to be tests that we write that check our code, and a series of tests to check our code under the conditions where if every single test case that we write passes, then we say that that code passes. And even if a single test case that we give it fails, we're going to say that that code fails because it failed on a single test case. Therefore, this is incorrect code. We have to get 100% on these things. We have to pass every single test that we give it to consider the code passing. And we should be thinking of every possible thing that can go wrong with a program to be able to thoroughly test a program. So looking at our large, medium, small method that we wrote, this compute size method, let's take what we had in that main method and turn that into a test suite. So here we're going to start seeing the syntax of how we run this automated testing and pick apart through how we write this. So this is what we call a test suite with one test with 3 test cases inside of that test. So what I call a test suite, I'm talking about the entire file. So in the homework document for each objective, I say write a test suite. If I said write a test suite named test compute size, that test compute size is the name of the test suite that I want you to write. So a bit of terminology there. And this test suite is going to test the functionality of the compute size method. That this uses Scala test, which is an external library. It isn't included with Scala or with Java. So this is something that we have to download separately, and we saw that in last week's lab. That's why we use the pom.xml. Inside that pom, there is a dependency for Scala tests, which tells IntelliJ to download Scala tests, link it to your project, automate that whole process, so we can use this library. If you get an error on Scala test right here, that means you have something with your pom.xml or with your Maven. You got to go through the Maven steps again. Yeah, that is Doggo snoring. You can hear him. I was hoping you wouldn't hear him, but yeah, he's sitting. He's right next to me over here. So let's pick this apart line by line and see what's going on here. So first, we're going to import everything from the Scala test package. We're going to use Scala's wildcard for this, which is an underscore. In a lot of languages, this is a star. In Scala, underscore, for what it's worth, it's just a different syntax for that. So this means import everything from the org.scalatest package. So in the library, their classes start with package org.scalatest. We want to import everything from that Scala test package, which is going to give us all the functionality that we need, all the classes and all the objects that we need. Next, we're going to name our test suite, and we're going to treat this as boilerplate for now. This is a class. We've created objects so far. This is going to be a class, which is actually used to create objects, and it extends FunSuite. FunSuite, short for function suite, is a class in the library, and when we extend it, we mean that we want to borrow all of the functionality of FunSuite. So test compute size is a copy of FunSuite, and then we're going to add more functionality on top of that. So we get a lot of nice features from FunSuite itself, like this assert method that we see, this test method, and it also controls the main method that we call. We will talk about this a lot more in Learning Objective 2, what class means, extends means. In inheritance, this is using inheritance. We will talk about all of that at length when we get to LO2. So you'll understand exactly what that line's doing. When we write a FunSuite, when we write a test suite, we don't write a main method. Inside the FunSuite class, FunSuite actually defines a main method that's going to be executed when we run this program. So we actually inherit a main method from FunSuite, and we don't have to mess around with that main method at all. We're just going to write our tests, and then FunSuite knows what to do with those tests. So we don't have to worry about writing a main method, calling our methods, etc. We're just going to borrow that functionality from FunSuite. When we write a test, we're going to use this test method, which we got from FunSuite. This is going to take a string, which is going to be the name of the test that you want to write. These names can be whatever you want it to be. I won't ever tell you what you have to name your tests. It's whatever you want to name them. I will tell you how to name your test suite because I have to call your test suite. That's how I'm going to call it, is by name. But the tests inside the test suite, you can name whatever you want. And they should be something descriptive that explains what you're testing in this specific test. And you can have multiple tests. I have a test here, but right down here I could start over again. Say test, give it a new test name, and then write code for another test. And then everything inside the test, that's what the code that you're actually writing to test your code. That's where we're going to add all of the checks and all of the test cases that we want to write to be able to see if this is working the way that we want it to work. And the big thing in there, so this is going to be just regular Scala code, whatever you want to code. And the big thing that we want to use is this assert method, again, part of the Fun Suite class. This assert method is going to be used when we actually want to check a piece of functionality. This is what we call test cases. I have 3 test cases here, an input of 70, an input of 50, and an input of 10. It's 3 separate cases that I'm checking. So for this, I want to assert and then give it a Boolean as the first parameter, or the first argument. And if that Boolean is true, that test case passes. If that Boolean is false, that test case fails. So if all 3 of these asserts, if all 3 of these resolve to true, then this test suite is going to pass this code. If any one of them is false, then that code, this test suite fails that code. It says this code is not correct. There's at least one test case, one assert that I checked that was false. So we want to check these 3 test cases. If they're all true, this is going to pass. We also have a second argument. This is optional in the assert, but I recommend it to help your debugging. And this is a string that's going to be, or converted to a string in this case. These are doubles, but they'll be converted to strings. They'll be toString will be called on them. And these are going to be printed out when the test case fails. So if this fails, this is going to be printed out to the screen. The lag isn't on my end. The ingest is just fine. That's something with your connection you have to check out. If it's too bad, just you can watch the VOD later if it's really laggy. So we're gonna run these 3 test cases, and if they all pass, our code passes. So this is the structure of a test suite. So let's head over to IntelliJ and make some more sense of that. Oh my IntelliJ, there it is. Let's get rid of this. Close that. And I want to check out this. Oops, my spaces went away. We have this test, and I want to run this to make sure that this test passes. So I like to right click over here and click run. I know you can't see that pop up, or you can click this button to run this test suite. So I'm going to run this test. Run this test suite. Yeah, slides are on the website. No, slides are on the website. And when I run that, I get a green check mark, which says the test passed. Everything passed with this. And let me just quickly... Oh my goodness, every time. I know why it does that. But it's not important to talk about. So I run this, test passes. Now if I go to my code, I'm going to do a control click here. Control click is going to take me directly to that, so I don't have to look through my files and find it. But this is the method that we're calling to test. And if I mess this up a bit, let's mess with this and say medium is 55. I'm going to close others and get just these 2 files open. And now I'm going to rerun my test suite. And now I expect something to break here. And now I'm going to get a test that's failing. So if I click on this, I can check what failed. And it's going to give me some output. Scala test is going to do its best to give us some information. And it actually gives us good information here. Small did not equal medium. So when I ran this test case, I was expecting medium, but I actually got small. And then it's going to print my hint, which is medium double, which is showing up right here. So this is printed out as a hint. to be able to give me some more information about the test cases that failed. So when this fails, it's going to give me that information. So now I have a failing test suite. It got to here, and actually once one assert fails, this one actually is never executed. The test fails right there and doesn't proceed. As soon as this fails, that's it. It's over. So our code failed. Nope, I got it right here. So our code failed that test, or the test failed the code rather. So let's put this to 35, which is also incorrect. Run this again. And my test is going to pass this code. So we arbitrarily decided that the boundaries are 60 and 30. I have code that chose 35 as one of the boundaries. This is wrong. This is incorrect code. But my test cases are so loose that my test case did not identify that that code is incorrect. So this is a problem. This is something we got to think about. That means that this testing is not thorough enough, which is something you'll hear throughout the semester. This testing is not thorough enough to actually test what we need it to test. What's up, Backsmasher? And yeah, the keyboard shortcuts are different for each thing, but I switched my control and alt on this keyboard. So the alt button is actually the control button, but I only switched it on the left side of the keyboard. So I get confused whether I'm using the left or right. It's just something I gotta update my stuff for. So that's where I get confused, where you see me fiddling around. So we can run those test cases. We run them just like our objects with main methods, and Scala test takes care of the rest. And then we get some nice output. We get the green check marks. We get the red text. We get the errors if we fail them. So we can know if our test case passes on our own code. So this testing is not enough. Here's a correct solution. And that test suite passes this. It says this is good code. It passes all three of my test cases. Here's an incorrect solution. And our test suite also passes this code. It says this is good code too. Well, we know this isn't good code. This is bad code. It has the wrong boundaries. It has 65 and 20, not 60 and 30. And our test says, you know what? That's good code. So we don't have good testing here. That's not thorough testing. So what we want to do is get more accurate. We want to make sure that any code that's wrong, any possible incorrect way of implementing this method, we want to write a test suite that's going to fail it. It's gonna that code is going to fail at least one test case of ours. So let's make this a little more strict, and we're going to go right up to the boundaries and test the boundaries of each one of these, of the large, medium, and small. So I'm going to write a test case right at 60, and I want to make sure that that returns large. I'm going to put one right at 59.99 and make sure that returns medium. So we only have a 0.01 variance between there that we're not checking, which, you know, we probably can accept that. Or we can just write more nines. If you want to write more nines, just go ahead and do that too. So, but we're checking right at that boundary. On either side of the boundary, are we getting the right values? We're doing the same with the other boundary. Right at 30, right at 29.99. Make sure we get medium and small respectively. So now that we're checking right at the boundaries, we're getting a lot better testing at this point. But is this enough testing? This is a question we're going to ask throughout the whole semester, and Autolab will let you know if you didn't do enough testing. Is this enough testing? And without Autolab, this is a big question you have to ask yourself all the time. Is this enough testing? Am I confident that if this test suite passes my code, that there's no possible way that my code is incorrect? So is this enough testing? That's a big question. And there's a good argument that this is enough testing. You could argue that, you know what, I checked the boundaries, I'm good, I'm fine with that. But there's also a good argument, and I would, for my purposes, I would like to add a few more test cases. There's a good argument for adding more thorough testing to this as well. What's up, Trino? So we could add more testing, and this is more of a thorough test suite that I would like for this question. For my purposes, if I'm writing code and I don't have an auto grader, I would want to write a test suite that looks more like this, just to absolutely make sure that my method is working correctly on all inputs. Do as much testing as I can to be able to get that functionality. So I'm going to use some data structures here. I'm going to create 3 lists. One list for inputs where I expect double, a list for inputs that I expect medium is the output, and a list where I expect small is the output. And just as an example, since data structures are still new to us as of Monday, if I want to add to this, I made the large doubles var instead of val, so I can reassign and add an element to it. Maybe I thought 1,000 wasn't enough. I want to add 10,000 as a large example. I want to add that to that. And then I'm going to use 3 loops, iterate over each data structure. Check all the large doubles, make sure they output large. Check all the medium doubles, make sure they output medium. You get the idea for smalls. And this is where printing out the input is a lot more helpful. This hint text, this second argument, is a lot more important here, because as I'm iterating over this list, if this line fails, IntelliJ is going to say this line failed. And it's going to try to give us some good information. It'll say expected large, large and medium didn't match. But I don't know what input those failed on. So if I print out large double, I'm going to know exactly which one of these inputs I failed on, and then I can start. My debug process, knowing where I have to look. Oh, I'm covering up some text again. Use data structures to run many test cases. So this is, I don't think anybody's going to argue that this isn't thorough enough. You can always go more thorough, but at this point, if code passes this test suite, in this case, you're pretty sure that that's correct code. It's possible that in the range, maybe on the input 100, it fails for some strange reason. But we're pretty good on testing on this one. So that's for strings. But for lecture objective 1, you actually have to test doubles. So we have to make sure that when doubles are returned, that we're getting the correct double. This poses a little bit different situation because we have truncation errors with doubles. Recall last Friday that we talked about doubles not being able to be represented in 64 bits. We're going to have some loss of precision when we store doubles. And specifically, here's one simple example where we have a value that's expected to be 0.3. But if we ask Scala, are these equal? They're actually not equal. They're not the same. They're not the same value, because when we multiply 0.1 with 3, 0.1 can't be represented exactly in a double. So we get a truncation error here. And when we do 0.3 like this, the truncation occurs in a slightly different way, just the way this multiplication goes through the CPU. These are going to be different values bit by bit. There will be some bits that are different, and this will be false. So to overcome this, when we're testing, if 2 doubles are equal, which we have to do for our unit testing, starting right with lecture objective 1, we want to check if the absolute value of the difference of those values are less than some very small value. So this is what we want to do when we're testing if doubles are close enough to be considered equal. We want to give it some variance, which is enough variance to allow for truncation errors, but not too much variance that's going to mess with the logic of our code. Like, we don't want to have epsilon being 0.1, because then we might actually be returning incorrect solutions that are within 0.1 and still being considered correct. So we got to be careful of what our epsilon is. I usually like 3 zeros about. Is usually good for my taste. And when you see the feedback in Autolab, I want to clarify the feedback a bit. So when you make a submission to Autolab, I will be testing your tests. To test your tests, I run your test suite against a variety of different solutions. Very very first thing I do is run it against your own solution, and I make sure your tests pass your own solution. This should always give you a smiley face, unless there's something strange going on. This should always give you a smiley face because you should be running your test suite against your own code in IntelliJ. And when you submit it, that should, you shouldn't submit if you're failing your own tests. And when you submit, you'll pass your own test. So I expect this to always be a smiley face. Then I'm going to run it against my correct solution on the server. So in Autolab, I have my correct solution. I'm going to run your test suite against that solution and make sure it passes that as well. If you don't pass the correct solution, that means there's something wrong in your tests themselves. You're testing some functionality that isn't what's specified in the problem statement. At least one of your test cases is testing something that's not what you're supposed to be testing. You're testing the incorrect things in there in your tests. If you pass the correct solution, we're also testing against a variety of incorrect solutions. So I'll have incorrect solutions, intentionally incorrect solutions on the server. I'm going to run your test suite against these incorrect solutions, and I'm going to make sure that your test suite fails those incorrect solutions. So if your test suite passes an incorrect solution, that means your testing isn't thorough enough, that you need to add more test cases and make sure that you're marking those incorrect solutions as incorrect code. So if you mark them as correct, you need to add more test cases, you need to check more things. Think about what more testing you need to be doing to make sure that you mark those as incorrect. And for each incorrect solution, I give you a very vague hint for each one of those. I give you a name, which is the directory name where I store the incorrect solution. I'll give you a very vague hint in that name as to what that incorrect solution is doing that's incorrect. The slides are posted, Lean. Slides are posted. Oh yeah, you might be getting cached. That's right. I only write slides next to the first few, so you know that icon means slides. But you click on the icon, that's where the slides live. So here's a lecture question. I don't want to spend too much time on this because I want to get to more examples in IntelliJ. But this was a lecture question. They're actually still using this in the other section, I believe. But I retired this one in my section this semester. But I had a question of compute shipping cost that given the weight of a package as a double, compute the shipping cost for this, where shipping is a flat rate of $5 plus 25 cents for each pound over 30. So anything 30 pounds or less costs $5 to ship. And as soon as you weigh 31 pounds, that's $5.25. If it's 34 pounds, that should be $6, a quarter for each pound after that. And fractions of a pound also count. So if it was like 3.1, you should also charge 0.25 cents for that extra pound. And write unit testing to be able to test this thing. When this is a lecture question, so I won't show the incorrect solutions except in this case. I do give the incorrect solutions for this lecture question, even when it was an active question. So in the other section, this should be shown in lecture, I would assume. That I have these incorrect solutions. So I run their code, run your tests against these incorrect solutions. All of these do something that's incorrect. Like, for example, the simple one, always under 30, treats every package as if it were a package that's under 30 pounds and just always returns $5 to ship this thing. So if you don't have any test cases that are under 30 pounds, you're going to pass this incorrect solution. Over 30 pounds. You're going to pass this incorrect solution, and you're going to get that sad face in Autolab. There are some other trickier ones. This one is the one that trips students up the most. Boundary over weight. The boundary, instead of being at 30 pounds, actually, no, this one doesn't trip students up because it's almost always wrong. Instead of 30 pounds, it treats the boundary as 33 pounds. Since I should have a 30 here just to make sure, but this is actually incorrect whenever you're over 5, the way I have it coded. Always over 30 is the opposite of always under 30. It doesn't, if you're under 30 pounds, it doesn't always return 5. It's always going to use this equation instead. So you're actually going to get a discount if you're under 30 pounds. So if all your test cases are over 30 pounds, you're going to mark this one as correct. And rounding weight. Oh, yeah, this is the one that trips students up. Rounding weight. I'm rounding the weight. So if you don't have any test cases that use a fraction of a pound, if they're all exact integers, even though these are doubles, if you always use integer inputs, you're going to fail this one because you haven't tested like 30.5 or 40.6 or whatever. So this one will get you. So you got to make sure you're testing a wide variety of different things to make sure you get all of my incorrect solutions correctly marked as incorrect from your test case. All right, examples in IntelliJ. This ends at 2:40. Yes. Okay. We got time. So let's go back to IntelliJ. Let's go back to IntelliJ. I have my other test cases here. We don't really have to. So this is Alt on this side of my keyboard. Yeah. I hit the exact same thing and it worked that time. Just to show off my test cases there. We already saw these in the slides, but we can run the whole thing. Assuming that I fixed, oops, I didn't fix this. So here I have 3 different tests. And it's going to show that the other 2, even though my first test, even though this test passed that code, my next test failed it right here on the input of 30. And my other test failed it right here. And this is where we need our hint. So we were expecting medium, we got small. And then I'm printing the medium double that we actually tested it on. So which one of these actually failed? It was 30. So we passed this one. And then when we got to this test case, we failed. So you get a lot of information here, and you get more information if you use these hint texts. So let's go to another example. And let's look at this string splitter method. We wrote this kind of silly, admittedly silly method that takes a string that's a series of Boolean values separated by semicolons and tells us the percentage of them that are true. This is the one we looked at in lecture. So we're going to split that on semicolon, count the number of trues that we have, count the total number that we've seen, and then divide the 2. So we want to test this method. So I'm going to write some test cases to test this, and we have a few extra things that we want to do here. First, our outputs are Booleans. Whenever I have this, I like to set up a compare doubles method, and actually give this in the handout for Pale Blue Dot. Just to get you started on testing. I won't always give that for later projects, but just since it's the very first lecture objective, I'll give you the compare doubles method. I like to set it up like this so I don't have to think about it too much. I just put that off to the side. I define a constant for epsilon. If you like the all caps convention, you can write this, name this in all caps too. And I choose some epsilon. 3 zeros is good for my taste for a value of epsilon. Now, when I'm testing this, I want to test this with a variety of test cases. And if we keep doing it the way that we've done in the slides, even like the lists weren't too bad, but the list only worked because we only had 3 possible outputs of the method. But now we have infinite possible outputs. Well, roughly infinite. 2 to the 64 possible outputs for doubles. We can't just have a list for all the inputs that we expect 0.8, etc. So here I'm going to pull out a map that's going to map inputs to outputs. And then I'm going to iterate over this map. Let me get the whole thing on screen here. Then I'm going to iterate over the map when I want to do my testing. So here's the test case that we saw in lecture. I expect this to return 0.8 because 80% of the values are true. When we have this input, here we got to think about our truncation errors a bit. 33%, 33.3333 repeating percent are true. So when I put my output, I don't have to have the exact, like I don't have to keep writing 3s until I'm tired of typing 3s. But I have to make sure I have enough 3s for my value of epsilon, for my choice of epsilon. So I want to make sure I go up far enough that epsilon is going to take care of whatever rounding I did. So I want to make sure I have enough 3s. I'm going to add one more just for good measure, actually, to make sure. Input of true, true, 100% true, 100% false, 100% true, so 0% true. When we're writing test cases, like for this example, this is a test case I want to make sure I have in there. So thinking about the testing that you want to do, and these are 2 test cases I want to make sure I have in there. It would be easy to write a solution to this method that doesn't handle single values, that doesn't handle just false or just true. If it's, for example, iterating through this string and looking for the first semicolon and then treating the rest of the string with different logic, that's a mistake that a developer can certainly make. So we want to check these 2. Another thing we'd want to test that I can't really test here because I didn't define the behavior, but what should the output be on the empty string? Should it be 0.0? Should it be not a number? Should, is that even a thing? Should it be not a number? Should it be positive infinity? I don't know. I didn't define what the output should be, but if the output is ever defined on something like this, you got to have a test case to check that. In a lot of the objectives, I will say if the input is the empty string, you should output this. If there is no possible value, return the empty list, things like that. Make sure you have test cases for those things, all those what we call edge cases, things that that can be wrong while having a mostly correct solution. When we want to run these test cases, I'm going to iterate over the keys and values of the map, and I'm going to name my keys and values something more meaningful than keys and values. Usually I'll use keys and values, but here the keys represent inputs, and the values represent expected outputs at those inputs. So I'm going to name those variables what I want them to be. Call my method in that string splitter object. Get the computed output. This is what my method actually computed as its output, what my code decided the answer should be. And then I'm going to call my compare doubles method up here to compare that computed output with the expected output to make sure that these are equal enough within epsilon to be considered the same double. So I don't have to worry about truncation errors. And then my hint string, I split, so we can put this all in one line. I split this into multiple lines so it's easier to read. My hint text here is going to give more information than I did in the slides. I wanted to know for this input, I expected this output, but I computed this output instead. Because when we have compare doubles, Scala test isn't going to be able to give us more information than that. And if everything goes well, I run this, and we should get green check marks because my code in this case is correct. And I want to break this. Let's change these to ints. So we were very careful to avoid integer division right here. But let's change these to ints. Run this again. Again, this arrow, this go button up here is always going to run the last thing that we ran. And now our test definitely fails. Fails poorly. And we can see our hint text now. So this hint text that I put on input, true, false, false, expected 0.33333, but computed 0.0. Now I fail most of these test cases, except these two, actually these three. I do fail this one, but notice that that wasn't the one that's printed out. And as soon as you fail one assert, the test suite ends. So remember, recall, you've heard this before, the ordering is not meaningful in a map. So when you have a map of test cases like this, you don't have an expected order in which these test cases are going to be executed. So this test case was going to be executed after this one. And these ones might have been sprinkled in. However, a few of them might have even passed. We don't know where they were. But we know that this one executed before this one, because that's the one that failed. And we expect both of those to fail. So for what it's worth, just keep that in mind. Map ordering, not important. To fix this, probably the quickest fix is to double that, and then we can pass that test again. In 5 minutes, we got this. Yeah, int divided by int is always an int. So when I had two ints divided by each other, the answer in this case was always going to be either 0 or 1. I can't have those decimals because an int can't have a decimal portion. So I was always either going to get 0 or 1. And then since I'm returning a double, Scala would compute the int and then convert that to a double for me. So the doubles that I get in the percent true were always either 1.0 or 0.0. So anything that wasn't a 1.0 or 0.0 was always going to fail. Speedrun, I thought I slowed this down a little bit today, but maybe not enough. I added examples too, so I had to go a little quicker to get them all. And finally, one more example. Any questions on that example? Let me take a quick pause. Any questions on that example? Can we see an example of this applied for Learning Objective 1? I'll do that after the lecture proper, during the Q&A. We can do that. Just because I don't have that project open, and I want to spend time opening it right now. How many application objectives will the next project contain? I don't want to answer that definitively because I'm not decided yet, but it will be more than one. There will be more than one on the next one. How many more than one? I'm still deciding. What do we do exactly in tomorrow's lab? Show up, and the TAs will take it from there. Is my quick and dirty answer. The more thorough answer is we're going to get you started on the project, and also give you some practice with the format of the interview and quiz next week, just so you know what the format is going to be and what to expect there. I'm just lost in general Blitzkrieg. We can help with that. We have office hours and hangout after lecture. I'll answer questions. And the review session tonight, 5 to 7. Be there. If you want extra help, be there. Ask questions. Get involved. Learn some things. My outputs are on one line. I'm not sure what you mean by that, Phantom. But we can talk about that after. All right, I got 2 minutes. Let's do this last example. Maybe I should have left more time for this. So I wrote this method, quick and dirty method, as an example. I actually wrote this right before lecture. Those of you who showed up to stream early, watched me write this one. Is I want to write a method that takes a list of ints and returns a map of int to int, which maps all of the values in the input list to their absolute value. So this is a good example of the accumulator pattern that you saw in 115, just applied in Scala. So we're iterating over a list. For each value, we're accumulating some values into a map. And we're accumulating key value pairs, which map the numbers of the list to their absolute value. And in certain cases, I personally like to add the parentheses. I left them off here just to show this example. But you can leave off the parentheses around a key value pair in certain cases. So I left them off in this case. I usually like to add them just to make sure nothing's going wrong, that I'm not messing anything up. So let's test this thing. For lecture objective 3, that method returns a map. So how do we test maps? How do we check if a map is correct? So for this, I'm going to create an input, 1, 2, -3. I'm going to create my expected output, 1 to 1, 2 to 2, -3 to 3, mapping the values to their absolute values. And then I'm going to get my computed output by calling that method on that input to figure out what my method returned. Oops, this isn't supposed to be dot equals. I was just showing that for example. So I have two maps, and I want to ask Scala, are these two maps equivalent? And to do that, it's a simple equal. So equal is going to check if these two maps have the same keys, and those keys all map to the same values. So for each key value pair, if the keys are equal, based on equal, Scala is going to check, grab both keys and check if the keys are equal to each other. So it's going to call equal all the way down. You have to be careful with this because if your values are doubles, your keys shouldn't be doubles ever. But if your values are doubles, it will call equal equal on them, and you're susceptible to truncation error. So you do have to be careful with this. This question was the lecture question in this example intentionally avoids doubles, so you don't have to worry about that. But if you had doubles, you got to be cautious about that. And that's, I think that's all I want to talk about for lecture. Actually, let's go back to the slides just real quick. So for lecture objective 1, that returns a double. Make sure you use a lot of precision. The incorrect solution for this uses a rounded value of pi. It just uses 3.14. And I actually have my test cases that are going to make sure you have enough precision, that you didn't use a rounded value of pi. But comparing doubles, make sure you use some epsilon that's small enough to not interfere with your logic. So you got to have it small enough to make sure that you're not using a rounded pi, and large enough to avoid truncation errors. For that one, like 5 zeros is probably plenty. Lecture objective 2, return strings. Compare strings using equal equal. We did that in the slides in that lecture example. And lecture objective 3 returns a map. So generate a map with all of the expected key value pairs that you want for the city names mapped to their populations as ints. And then check if those maps are equal to the one returned by your method.